Hello, welcome to session 20 in the series Analog Circuit Design using ADS. My name is Anurag Nigam, and till now we have seen on-chip bias circuit, which we are going to use to bias various transistors on the chip. Right. So now, one thing I mentioned is that we can reduce the number of transistors in a bandgap circuit. And what is that? That is called Brokaw cell, right? So in Brokaw cell, the design is the same. There's nothing much different. You can just take the design and turn it into a Brokaw cell. Now, how do you do that? Go back to the bandgap circuit and say copy cell, and I'm going to say this. I'm going to rename this as a Brokaw. Okay, cell. Okay, so once I have done that, okay, so there's the Brokaw cell. Now to modify this, all I have to do is everything remains the same. It's just that I'm getting rid of these transistors, right? So the design looks much simpler than what we had. And then what I can do is I can remove these grounds and take this and put it here. Okay. Even I don't need this transistor, right? So all I need is this resistor. Okay, so all I need is this resistor, which I'm going to place here, and that's it. That's my Brokaw cell. And okay, so what's going to happen is, so this is gone. Okay, so this transistor, so now you see that the slope has been readjusted. So what's going to happen is we have to adjust the resistor sizes. Okay, so this circuit is basically the CTAT, while this circuit is the PTAT. So CTAT plus PTAT is still a band gap, right? So all I have to do is adjust these resistors. Okay, that's all I'm going to do here, right? So this has simplified a lot, and I'll tell you the thing is that the band gap voltage is going to be this voltage, or rather across this transistor. So I can say this is the band gap, and this will be higher than band gap by VGS. So I will call this as V band. So I'll call this one as V band. Right. So the circuit is simplified. I'm going to hit a simulate with a tune. Okay. Yes. So this is a Brokaw cell, right? So I'm going to plot here V band. Right. This is not what we expect. Of course, there is a tuning on, and I will adjust the size because the CTAT transistor has become smaller, right? Okay, so that's the reason. So I'm going to go here and look at the tune here, and meanwhile I'm going to look at the output here. Right, so these resistors have to go down. Okay, so both these resistors have to, so basically this resistor has to go up to reduce the slope, while this resistor has to go down. Okay, so there we are in the known turf. So again, this is a CTAT resistor. That resistor has to be lowered. So let's see. So let me just fine tune this one. Okay, and this one, the slope has to go up, so this resistor has to come down. So this resistor has to go down for the slope to go up. And this resistor CTAT, right? This resistor has to go up. And this has to go down a little. There you are. Okay, so this is our response, and I'm going to update this and say close. Yes. So here we have the same response what we had earlier across temperature, right? So this can be used as a band gap source. So now what I'm going to do is I'm going to turn this one into a what you call a component, so that in my linear regulators or voltage regulators I'm going to use them, right? So I'm going to just copy this. So I'm going to just take the Brokaw cell and say make a copy of this and put a C here to remind me that this is a cell which I want to use, a component. And here I'm going to go and throw these components and put in. So this will stay there, and this I'm going to remove. This DC I'm going to remove, and this is my ground, so I'm going to combine all the grounds. Right, so this is the ground. Supply will go away, so this is 3-volt supply. Right, so I'm going to connect these like this. So this is our startup circuit, and this is VDD, right, and this is ground. Right, so everything is very simple right now, right? And the resistance is halved, and the reason for that is because in this the current is going to be twice of IPTAT. That's why this resistance got halved. So if you understand the difference between the regular band gap circuit and this Brokaw cell is, this is seeing twice the current, twice the IPTAT. That's why its value got halved, and then RS value is almost the same as what it was, right? So we just slightly adjust these resistors and got the band gap. Now there would be an output we will call as V band, right? And that pin is over here. And of course it is capable of driving some current also, because there is a beta helper here, so you can always pull the current out of this node, right? So that's the slight advantage you're going to have, is there is a beta helper to help the current going out. So I'm going to make a symbol for this. Right, and this symbol is going to be very simple. So that's our Brokaw cell. Okay, so I'm going to just cancel this. Now what I'm going to do is I'm going to do a simple linear regulator. You can also call it LDO, right? It works on the same principle as linear regulator. It's a linear regulator with a low dropout voltage across a pass transistor. So I'm going to make a new schematic, and I'm going to call this one as LDO. LDO. And there are different kinds of LDOs, right? But I'm going to cover just one very simple kind so that people can understand. So create schematic. So first thing I need is a Brokaw cell component. Second, I need to just flip this around like this, and I'm going to move the text over here. Okay, next is I'm going to take an op amp. A two-stage op amp will do, because I'm going to use MOSFET rather than PNP transistor for the pass transistor, right? So I am going to just mirror this out like this, and this is my inverting terminal. So I am going to connect the inverting terminal to the reference. Okay, and then I have got a pass transistor. So in this case I can go inside and borrow a PMOS device. So let's go inside and pick up this PMOS device, edit, copy, come up in the design hierarchy and say edit, paste, and then I'm going to rotate this. Okay, so now I am going to, okay, the source has to be always at the known potential. That's what we have discussed till now. The source is at the known potential. I am going to make it a 130 nanometer as a gate length, and this is going to be, let's say, 10, or rather 5 will do also. Let's do a 10, doesn't matter. And the number of fingers I'm going to put as 160. So this is a 1600 or 1.6 millimeter device. Now why this transistor is large? Because I want to support a certain current, and this error signal is going to be controlling the bias on the pass transistor. And then, so let's move this up, and then I am going to put in here a resistive divider, right? So I am going to go here to lump components, pick up this and rotate it out. Okay, so this I am going to put as 20 mega ohm. I don't want to draw, because I have to just generate the voltage reference. So I am going to put very large resistors here, 20 mega ohm, and then I am going to put here something like 40 mega ohm, and that is tunable. That is to adjust the output voltage. Now I'll tell you how it works. Okay, so this is the resistive divider, and this is, let's say, 40 mega ohm. Okay, so this is a known voltage. Okay, why I'm saying this is a known voltage? Because the output of this is 1.19. so because the gain is very high, then it has to be 1.19 here, then the error signal is going to be 0. So what I'm going to do here is, so this voltage is 1.19, so this voltage is 1.19. So that means that the lower limit on the output voltage is going to be 1.19. Now if you want a still lower limit, you can put a level shifter in here that will control this, so you can still bring down that limit, right? Now, or you can put a level shifter here, right? So you have to shift up the voltage here, or you have to shift down the voltage here. Anyways, so this is the output, and this is going to be the bias for this, and this is going to be the ground. So I need a 20 microamps of current for the MOSFET, for the op amp. 20 microamp. Sources frequency domain. Where did it go? Here. And this would be 20 microamperes, and these are connected together to ground. Right? So I'm going to do this as 20 microamperes. Okay, so we are all set with the design now, and then I'm going to add a load. Right, so this is a ground. So this is my linear regulator, and then I'm going to add a load of something like 100 kilo ohm or something. Later I can change the load and see what is the output voltage. So go to lump component and add here 100 kilo ohm. Later I will show you that it can be reduced to anything. Okay, so now I also want to keep a notice on what is the output current, right, and the output voltage. So I'm going to keep here a probe component. Probe component. Why does it say that always? Say rotate it. So this is going to be a IO. So if I reduce the RL, right? If I reduce the RL, then the IO is going to increase. So I'm going to draw more and more current into the load, but the voltage is supposed to hold constant. That's the whole idea. The voltage is supposed to hold constant. Okay, so this is done. So I'm going to name this node as output node VO. Correct? So I want to see whether it acts as a regulator. What about the supply? I am going to put here a 3-volt supply. A 3-volt supply. Later I'll put a tune on this supply also to see how is the line regulation. Okay, so this is the simplest LDO I can make, and here you can also do overcurrent protection on this node and stuff like that, right? So you can do a overcurrent protection here, put a circuitry for overcurrent protection, which will switch off this MOSFET when the current drawn increases to a limit. So I'm not going to go into details of LDO design. There are different things can be added to this LDO, but this is the simplest LDO. Okay, so I need a include file. So that's the include file, and I need, so temperature of course is going to be controlled by this. So it is a temperature compensated bias circuit. So I'm going to assume a flat response across temperature. If you want, you can adjust the slope of this circuit. You know how to do that. Adjust RS and RD so that the overall response can be flat. You can do that. You can make a pseudo PTAT or a pseudo bandgap or whatever you call it. Okay, so now I want to see its performance. So I want to do a DC analysis on this. So I will go to simulation DC, and here I want to look at the output voltage and current, and also I want to see what is this node doing. This node should be 1.192, whatever is this node, or 1.194. So these two node voltages are going to be same, right? So I'm going to put here name of the node to be VREF. So VREF should be same as the bandgap voltage. So we are ready for simulations, right? So I am going to simulate this, and I'm going to just look at the corner cases. Okay, so here I'm going to put VO. Okay, 1 point some voltage, right? And then I'm going to put here VREF. VREF will be 1.19. It cannot be different. So this is 1.196 as expected, right? And then I want to also look at the IRF, IO. Okay, so this will be current in milliamps. So if you want, I can put it on the right axis. Okay, so this is drawing 35 milliamps at present. Okay, so now with this, I am going to put here a marker too. Marker new. Okay, so this is our current in milliamps, and I'm going to put this in format engineering. So I'm drawing 35 milliamps here. My output voltage is 1.79. So let's put this voltage to the minimum possible. So what I'll do is I will put a tune on this one, so this will adjust the output voltage. And how does it work? It works the following. Okay, so V out, sorry. Okay, so VO would be equal to Vref divided by this RCNTL. Vref by RCNTL is the current times of, so this current is going to flow through both the resistors, right? So this, okay, so basically this output would be CNTL plus the 20 mega ohm, right? R1. So let's say that R1 is 20 mega ohm here. So now if I want to generate a certain voltage, I would have Vref, and this will multiply it. So I will have Vref plus Vref into R1 by RCNTL. Sorry. Oh. RCNTL. Now, so if I have a desired output voltage, then I can have V out minus Vref divided by Vref, okay, should be equal to R1 by R control. So it will be R1 by RCNTL. So I would have RCNTL should be equal to R1 divided by this term, so it will be Vref divided by VO minus Vref. Okay, so this is going to break down. So if my VO becomes equal to Vref, R control should be very high, infinity actually, right? So that relationship breaks down here. But then if you want to have anything above Vref, so VO is larger than Vref, so for VO larger than Vref, I can compute a R control, right? So if I have VO close to VDD, then R control will be the smallest. And if we have V out close to Vref, right, then R control should tend to infinity, and in this case tend to 0. So if you reduce R control, the output voltage is going to be high, and if you increase R control, the output voltage is going to be low. So that's the basic relationship. And then for a given, for whatever VO, right, there would be a limit on the maximum current, or there will be a limit on the power, right? So where does that limit come from? That limit comes from A, the supply voltage, B, the current capability of this device. The larger the device, the more the current it can let through, right? So the size of this transistor is controlling the current, and the voltage is controlled over here, right? So that controls the power. So with the least voltage VO, the current can be high, and with the maximum voltage VO, the current can be low. right? So now will the two powers be same? No, because when the current is high, the overdrive here is high. So the transistor will be dropping out that overdrive across it, right? So as the current is high, the overdrive is high. Okay, that means that it can deliver lower power when you have a VO as high. If VO is low, okay, current is it is capable of more current. Sorry, if VO is low, it is capable of more current. That means that the overdrive is going to be large, so dropout is going to be large, right? So that's how it works, right? Okay, so now the two powers should almost be the same, but they will be slightly different, right? Okay, so let's see what's happening over here by putting in a tune. So let's here put a simulate, and here okay, it has come up with RDRS, which is something inside. Just one second, let me go here and disable that tune. Okay, so these guys are tuning, so this has to be disabled and this has to be disabled because I want this voltage to be fixed. This is a band gap reference, so this is done. Now here I'll put a tune. Okay, so this is going to, of course I should have put here exit tuning mode. Yes, so I will first start with the 50 kilo ohm, not 50 ohm. Okay, so here I am going to put a tune on the load. Okay, so this is going to decide, R3 is going to decide the current, then this is going to decide the output voltage, and then I would see what is the line regulation. So I'm going to change VDC also. For now VDC is fixed. Now let's see what is happening to the output. So right now it is at 1.79 volts, then this is 1.196, and then the current is 35.9 this. So let's increase this resistance 40 mega ohm up to something like 160. Okay, so large value is that, and the lower value I'm going to put as 14 or 15, right? So now let's go below. So this is going to go close to 3 volt or VDD minus V overdrive. So right now it is 2.9. With the least value it is 2.9. And with this I want to see what has happened to my band gap. My band gap is rock sturdy here, right? It's not doing anything. Now let's see if I start loading this with lowering R3. Okay, so how much should I lower R3? Should be like, so this is 1 kilo ohm, right? So even I want to go below 1 kilo ohm, so I'm going to go 0.01. So this will be like 10 ohm, right? Yeah, so let's increase the current. So notice that the output voltage is constant. So if you see, let me put here your things to notice. So this is my output voltage. Okay, I will adjust the grid. Preferences, grid snap 1. Okay. So this is our output voltage. Okay, and Control C, Control V. This is our reference. So notice that reference has to hold constant. If reference doesn't hold constant, then output doesn't hold constant. And this is the loading. So this is the current. So for current I'll put a red colored line here. So this is our current. Okay, so let's check. This is the high voltage, right? So keep lowering the load and the current is going to go up. So at present it is 200, and so you see here my band gap is affected here. So let's go up here, 0.01, 10 ohm. Okay, so I don't want I will go to a limit where my band gap holds solid. So up to here the value is 30 ohm. So 30 ohm, with 30 ohm also the band gap is holding 1.195, output is 0.29, the supply is 3, so there is a dropout of 0.1, and the current is 96. Okay, now the current is 143, and I am seeing the effect on the band gap, and the output is going down. Okay, so at 2.9 I could deliver 143. So let's put down a power high with high voltage, right? So PWR underscore H is equal to 143 into 2.9 into 143. Okay, so let's put here the design. Alright, so it is able to deliver 0.5 watt. Okay, so let's see if I was to make this one. So let's just update this. Update, close. Okay. Okay, so here let's slightly increase the size. 1.8 mm device. Let's go here. So let's slightly improve the output voltage, reduce it, I mean to say. So this is your load, right, and this is your voltage adjustment, right? So this is 1 mega ohm, for example, and this is 15 right now. So 1.9, 1.8, sorry, 2.9, 2.8, 2.8, and right now I'm drawing a current of 1.5 kilo ohm, is it? Okay, so this has changed. What happened to my currents here? Marker 3 is the VREF I out. Okay, so let's bump up the current by lowering the load. Okay, so right now it is still holding. This is 275, so now it is not holding. Sorry, this is going to be 10 ohm, still holding. So it is holding under 10 ohm. So this is going to be 2.8 roughly. Holding is 275. Okay, so 770 milliwatts. So this is what happened on the higher side. Let's see what happened on the lower side. So I am going to take the output voltage to be low. How low can be low? Let's say 1.3 volts. Okay, 160, 180, Okay, 1.33, 250. Okay, so I'm going to stop at 1.3. Okay, now VRAF is rock solid here, right? So that's a good thing. And now I'm going to bump up the current. So right now the current is set by this. What is this gonna do? 1.3 volts. So it should be around 1 ampere current, right? If I go 1 ohm. Yeah. So is it holding? No. Okay, so I need finer graduation here. So right now this is 1 ohm. It's around 1 ampere current. This is 2 ohm. 2 ohm it's holding. 2 ohm is holding it here. And this is 1.3. So let's put out what is the power delivered at low voltage. So I'm going to put here low, L for low, and I'm doing from 1.3. 1.3. Correct. And what's the maximum current I can put through? Let's put here still further. Okay, so now it's still holding, it is still holding, it's still holding, not holding. Okay, so at this point it is drawing 1 amperes of current. So the output is drawing 1 amperes of current. So here this is going to be 1.084, 1.08. Okay, so this is going to be your, at low power, what is the peak power it can deliver. So low voltage, what is the peak power it can deliver. Okay, so it goes from anywhere from, at 2.8 it could deliver 770 milliwatts. At 1.3 it could deliver 1.4 watts. Okay, so the dropout voltage can be as low as 0.2, right? So this is a example of a linear regulator, and the current drawn has no impact on the output voltage. Of course, a very little impact, but in this region, if you see, when you go a certain milliohms, micro, now you are in the milli. Okay, so here you see the output voltage is very sturdy, 1.3 volts. Okay, so this is the simplest circuit to understand how this LDO is working, right? So what I have shown you is a circuit which is based on an op amp and a voltage reference, and I have generated a voltage which is almost independent of the loading, but then there is a limit on the power which it can be delivered from this 3-volt supply. You can also see the variation in this one, so let's just see that also. So let's go here. Okay, so let's say this is 0.1 volts. So let's say this is 3.3, 3.31. What happened to, let's look at the output. Okay, 1 point. So this, of course it changes slightly because VRAF is changing, right? But this also has a certain line regulation. Now you can figure out how good is the line regulation, right? So 1.3. So as long as your VRAF holds constant, you are okay. Okay, VRAF holds constant, VO is going to hold constant, and then you can see if there is a ripple on the supply, that will be taken care of. Now this is a very simple design. This is just to understand how a LDO would work, but then you can add more complications to it to make a much better performance. So I'm not going to cover that. I just wanted to cover a simple linear regulator. Okay, great. I'm going to stop here. Thanks a lot.